before Jackson gave his comprehensive exam presentation, I wanted to give a little bit introduction. Then the procedure will be, he gave a presentation around 45 minutes, hopefully. And then the public can ask any questions. And then we will have a closed door examination in the second hour. So I first learned about this name, Jackson Jandreau, right before Christmas in 2018. I was working in Antarctica, then I suddenly got an email from Jackson. He said he's graduating from Oklahoma State University, and he wants to do the science stuff. So I emailed him back and said, do you want to come to Antarctica? Then he answered yes. So I said, okay, I have a PhD position for Jackson. Jackson is a very unique student. First, let me give you a joke. He sensed the troubles with Boeing 5 years earlier than the news media. He can tell you the story. And the main, what is the trouble? Jackson had a undergraduate partner when he did the river over in 2023 last year. That student's name, Jack. Jack graduated with a bachelor's degree this May. And we asked him, have you found a job? And then Jack said, I'm moving. Jackson said, you can easily find a job in Boeing. Then Jack answered, yes, as long as I keep my mouth shut. So you guys know about at least two whistleblowers, had some strange thing happen. So Jackson had a very strong motivation for going for science discoveries. So he has been working with us nearly 5 years. And during this time, he has done lots of things, including either, expedition in Antarctica, development of some innovative techniques. And now he's using all these tools to study the graduate dynamics. So this time we invited 9 committee members, Professor Palo and Professor Jack Fox. They have gone through this common exam with Jackson last Monday because they are out of country. This week. So we still have another the committee member, John, Han Li, Eric, Hans Peter, and also Dr. Chad Gardner. We have one more committee member, Dr. Sharon Wallace. She is out of town today, so she's going to meet Jackson tomorrow about it. So for Jackson's study, two special things I wanted to mention. So in your evaluation of this exam proposal and the presentation is one is we went through COVID. So this is day-to-day is Antarctica deployment for pretty much two years. Yeah, 2 years. And another thing is I don't know whether Hans Peter, you are aware of that. For 6 years, I didn't have a LiDAR observatory around COVID. Yeah. Now forbidden us from going to Table Mountain unit. Seriously, it took us about 6 years. Finally, got the LiDAR observatory by the end of 2023. So you can think of that. This is a very difficult time for training students. But Jackson, even under such harsh conditions, Jackson, eventually get himself up, and we did the restart of McMurdo LiDAR campaign because we were gap. We had a gap for 22 months. For lasers, you drive too hard, it will break it. But lasers, you don't use it. Nobody touch it for 22 months, it will break too. So he did lots of preparation work helping. He's pretty much act like a postdoc. And we together with other students, we got this restart very successful in 2022. Then he stayed over 14 months on the ice to do the winter over, and they did one of the very best winter. So he has lots of story to tell. One thing I want to ask a committee member to help me to decide today is, this is a very ambitious guy. He proposed so many topics. So the question is, how many more years you want to work on the PhD? Or you want to become a PhD, then work as a postdoc? So I Of course, every member has different opinions, so we hope to get some good advice, help Jackson to shape up his plan for the PhD dissertation. So it's all yours, Jackson.
Okay, awesome. Thank you, Dr. Chu. So thank you everybody for attending today. And or attending on Zoom. And if anyone's watching this recording later, I think Sharon may watch it. Thank you for attending then. So my name is Jackson Jandreau. As Dr. Chu said, that was a good intro. I don't need to tell you too much about me, so I'll just get right into things. So the title of my proposal is LiDAR Expedition in Antarctica, Development of Bias Elimination Techniques and Exploration of Gravity Wave Dynamics with Observations and Models. So there's a couple different aspects of this that I'll dig into in a couple slides here. So make sure this works. Okay, so starting out, I'm just going to give a brief introduction to all this work and the work that I've done with the group. And then I'm going to dive into the LiDAR expedition that I've did my interaction with the McMurdo campaign and my season at McMurdo. Then I'll go over my work to help develop bias elimination techniques for helping process LiDAR data. Then I'll dig into the exploration of gravity wave dynamics using this LiDAR data, and then I'll show you my summary of all my proposed work. So to start out, the polar atmosphere is a really complex picture with a lot of complex energy inputs. Due to source, it's got sourcing. There are energy sources from both above and below, as there is elsewhere in the atmosphere. However, the poles have unique energy inputs, such as field-aligned currents and solar energetic particles, joule heating, auroral heating. These are sources that are not present elsewhere on Earth. So while the atmosphere is already a complex picture, at the poles, it's even more so. One of the major sources of energy entering the polar atmosphere from below is through gravity waves. Gravity waves are a large source of energy, driving residual circulation and adding momentum and heat and all sorts of things into this portion of the atmosphere. Additionally, recent trends in polar climate continually show abnormal behaviors, such as I put a little plot here that shows, I believe this last year was one of the lower, it's like the fourth lowest sea ice coverage we've seen in observed history for the Northern Hemisphere. So all these studies that come out every year about this polar regions just emphasize further the fact that we need to continue studying these regions, and studying gravity waves will help us better interpret what we're seeing in these polar regions and help us model them better and help solve some of these problems that we're facing. So there's many different ways that you can observe polar gravity waves, everything from in situ measurements to measuring from above with satellites or measuring from the ground with things like LiDAR or radar. So LiDAR is one of the more capable methods by which you can study LiDAR is one of the more capable methods by which you can study these polar gravity waves due to its spatial and temporal resolution and the fact that ground-based LiDAR can sit undisturbed on the ground and measuring the same volume of atmosphere continuously for days and in theory months on end, given good observation conditions. And because of this spatial resolution and because of this ability to take long measurements, you're able to cover the full spectrum of gravity waves from inertial to buoyant. So LiDAR are able to observe the full range of gravity waves, but also other things other than gravity waves, LiDAR can also measure at the same time. So I put a few examples here. Real quick, that's our LiDAR down at McMurdo Station, Arrival Heights in the bottom left. You can see the 589 sodium LiDAR beam, which you can't really see on this presentation too well. Maybe right there, you can kind of see is our two UV beams. They're barely visible, and cameras can even barely capture them. But there's 3 beams coming out of the roof of this building, and from all those LiDAR, we're able to measure some of these different things we see here in the top left there. In the top left there is the TIFE, the thermospheric extensions of the atmospheric iron metal layers that was discovered by Dr. Chu in 2011. Some persistent gravity waves, which were observed for the first time down in McMurdo. And that figure is from Chen et al. 2016. And then in our most recent year, this is not published yet, but these are volcanic aerosols from the Hunga Tonga volcanic eruption that have been transported down to McMurdo, and we observed them in our LiDAR. So these LiDAR are able to study many different things in the atmosphere, so they're very, very capable instruments. So gravity waves are, as I mentioned earlier, gravity waves are a really important source of transporting energy from the lower atmosphere up to the higher regions of the atmosphere. So gravity waves are formed by any disturbance to a stratified atmosphere in the ocean and the atmosphere. Of course, here we're going to be focusing on the atmospheric ones, but this can be anything from flow over orography, continental shelves, that sort of thing, continental shelves or mountains, that sort of thing, convection leading up into the upper troposphere or even lower stratosphere in generating gravity waves from that convection, but also things like interactions between planetary waves and adjustments of the polar jet. Other sources can form gravity waves way up in the atmosphere as well, such as joule or auroral heating has been shown to form gravity waves. So They can be formed by many different mechanisms, but there's also new mechanisms that are being discovered and studied more and more as this field evolves, such as secondary gravity wave generation from gravity wave breaking, which I'll go into significantly later on in this presentation here. So it's important for us to study these gravity waves. They're a major driver of, as I mentioned, they're a major source of transporting energy from the energetic lower troposphere up throughout the entire atmosphere, being responsible primarily for the driving of zonal circulation. The wave drag by these gravity waves is responsible for zonal circulation in the mesosphere, so very, very critical in that region, but also for all these other regions as well. As we continually make use of the ionosphere for communication purposes, satellites, radio communications, and that sort of thing, it's important that we understand the role these gravity waves play in generating TADs and traveling ionospheric disturbances that these gravity waves introduce, which can disrupt these communications. So it's important for us to understand these gravity waves for that aspect as well. And also these gravity waves play an important role in driving global circulation, such as the quasi-biennial oscillation. So now to introduce the McMurdo campaign and talk a little bit about my involvement in it. So the McMurdo campaign started in 2011. It's been started in 2011 and operated until 2020, where we had to stop for NSF COVID pauses, research COVID pauses, and then picked up in 2022, and it's been operating since then. The iron Boltzmann LiDAR was installed in December 2010, and the sodium Doppler LiDAR was installed in 2018, and both of them have been operating ever since. And over that time, since 2011, we've captured over 13,000 hours of data. That's the 13,000 hours of good data, including 2,500 hours during my season. So why are these? The first question I always get asked when I tell people we have these LiDAR down there is, why are we operating these LiDAR at McMurdo? It's not the easiest place to operate. The initial reason that this LiDAR campaign placed itself at Antarctica is it followed a chain of measurements that Dr. Chu and Dr. Chet Gardner had done with this LiDAR at the South Pole and at Rothera. So McMurdo filled in that latitudinal gap right between the two, giving a nice chain of latitudinal measurements where you can compare the results from this LiDAR. But also the polar darkness you get at Antarctica, you're well within the polar circle. So you get 4 to 5 months of pure darkness, meaning that you can take long LiDAR observations without having to take long LiDAR observations under the optimally dark, high signal to noise ratio conditions that environment provides. But also, other reason McMurdo is especially useful is its location with respect to the auroral oval. During certain parts of the year, you are within the auroral oval with high auroral activity. In other parts, you're outside with no auroral activity. So you're able to kind of get more bang for your buck with your location by choosing this sort of location. And also being in the poles, just measure polar stratospheric and polar mesospheric clouds, which have implications for climate change and are a pretty popular topic of study. Just real quick, this McMurdo campaign's had quite a few major discoveries, such as the thermospheric extension of metal layers and these persistent gravity waves I showed on that last slide. And that's not an exhaustive list. There's been tens and tens of publications from this result and multiple PhDs out of it as well. So to introduce the iron Boltzmann LiDAR, this LiDAR consists of two transmitters operating at two almost identical transmitter LiDARs operating at 748 and 744 nanometers, which are both doubled to 374 and 372 nanometers. These two wavelengths are shot out of our building they travel up into the mesosphere and lower thermosphere, the MLT region, and probe two energy levels of atmospheric neutral iron. And by comparing the return signals from those two energy levels, we're able to determine the population density of those two energy levels is determined by the temperature of that atmospheric iron, as you can see from the Boltzmann relation up there. So as we compare the two energy levels, so the returns from these two energy levels here, we can back out the temperature. So ultimately, this LiDAR is able to determine atmospheric temperature, atmospheric iron density, but also by analyzing the Rayleigh scattering off of atmospheric oxygen, or atmospheric O2 and N2 in the lower atmosphere from about 30 to close to 70 kilometers. We can also back out atmospheric temperature and atmospheric density from this. And so ultimately, all these tracers we can study, there are cases in which it's very useful to study the temperature for its own principles or the iron density for its own principles. But in my case, what I'm doing with all these is I'm using them as tracers to study gravity waves. So the sodium Doppler LiDAR is also similar. It's similar in some ways, but instead of having two different transmitters, it has one transmitter that is split into three different frequencies using acousto-optic modulators. So we shoot out three different frequencies centered around the central absorption band, the D2A band of absorption for atmospheric sodium. And by probing at three different wavelengths, we're able to assess the broadening or narrowing of the atmospheric sodium spectrum or the Doppler shifting of it. So that broadening tells us about the temperature of that atmospheric sodium. The shifting tells us about the radial velocity of that atmospheric sodium, which in our case corresponds to, this is a vertical pointing LiDAR, corresponds to vertical winds. So ultimately, this sodium LiDAR is able to derive atmospheric temperature, atmospheric vertical winds, atmospheric sodium density, and also we can process the Rayleigh to give us temperature in that lower region and atmospheric density in that lower region. Oh, and again, the main thing I do with these tracers for my work, there's a lot of work that's done by our group that studies these tracers for their own merits. But in my case, most of the time I'm using these to study and trace atmospheric gravity waves. So my PhD is sort of a multifaceted approach, as Dr. Chu introduced earlier. And that's not to say every PhD isn't a multifaceted approach. I've yet to meet a PhD who doesn't have many different fields coming together to accomplish whatever their science goals are. But I feel like mine has a little extra aspect to it that I think makes it unique. As Dr. Chu mentioned, I've been able to get my hands on the management of the LiDAR campaign from not just from the inside as an operator down there operating the system, but also I've been able to participate in the logistics side of things, the planning, working with NSF, helping write the grants, all of those sorts of things. So I think that's a really unique aspect to this PhD that other students might not. And of course, in addition to that, that's in addition to helping develop the LiDAR technology, processing methods, operating the LiDAR, and all of that sort of thing. So I just want to kind of run through the general layout of my PhD. So like I said, learning the LiDAR technology and how to manage a LiDAR campaign. Doing that for the last couple of years then led into me operating the LiDAR campaign from 2022 to 2023. Then while I was doing that along that route, and especially during those 2 years where we weren't able to access the base, I worked on developing LiDAR processing methods. Then once those methods are well developed, I'm able to take those methods, use them to process a lot of this LiDAR data, process the entire, all 13,000 hours of this LiDAR data, turn them into usable, accurate LiDAR atmospheric parameters, and then finally take those parameters, process them, and use them to make meaningful, relevant scientific discoveries. So that's sort of the layout. Now, Dr. Chu pointed out a Confucius quote to me I wanted to share here, which is translates to if a craftsman wants to do a good job, he must first sharpen his tools. So that's kind of the layout that I'm doing here. Is I thought it might be fun to try to say it in Chinese, but I would have butchered it, so I didn't. That, yeah. So anyway, that's kind of the structure that I'm doing here. Is first, I'm sharpening my tools by refining these data processing methodologies, and then I will be applying them to accomplish my good job as a craftsman or worker. So to go into the 2022 to 2023 season, I won't spend too long here. Dr. Chu introduced it pretty well earlier, but this was not a typical season. It was following a long break. We didn't really know exactly what we're going to see on the ice. So it was a lot of prep that went into getting ready for the season, ordering spares of almost every single part that is involved in each of these two LiDARs. And even then, we didn't even have every single part we needed once we got down there, but also training on different things that could have gone wrong in the time that we were not there, such as the reflectors degrading on the YAG laser. We planned on how to clean, polish, and refurbish those. So there was a lot of work that went into getting ready for the season. Ultimately, it was successful. We did not have too many things when we got down to the ice that we weren't prepared for. And overall, the season was able to, we were able to get the LiDAR perfectly refurbished pretty soon on the ice, collect a ton of data. As I mentioned, collect over 2,500 hours of data, which is like double what a typical season gets. And there was a good portion of the season where there were more LiDAR team members on the ice. So I can't take full credit for that myself, but Jack and I, this is Jack Irigaran, he wintered over with me. Him and I were able to collect over 2,500 hours of LiDAR data. And so also my own personal time on the ice was 441 days. That is, there's not a hard rule for it, but they say 450 days is when they kick you out so you don't go crazy. So it's getting close. So now to introduce my work with helping develop bias elimination techniques. So I feel like data processing methodology is very important, as it not only benefits future data and the current data you're collecting right now, but you can also take that processing and apply it to previously collected data. If you do work to develop the technology of a LiDAR, you're improving those future measurements, but this has compounding effects. You can, and so even though these methodologies weren't developed until 2019 to 2020, we were able to apply them to the last decade of LiDAR data. So whenever you use any kind of instrumentation method, such as LiDAR or radar, there's going to be an inherent bias in that data. With LiDAR, it's due to Poisson distributed noise in the photon counting process. That's going to establish itself as noise in your parameters. So let's look at the anatomy of what these look like. Let's say we're taking atmospheric temperature. It's going to have that noise on it. atmospheric temperature perturbations, I should say. So we subtract the mean. There's going to be a portion of that perturbation caused by the waves and a portion of that perturbation caused by the noise. Obviously, the noise perturbation is not real, and you would prefer it not be there. But this noise parameter, the noise component of this perturbation is mean zero. So if you average enough samples together, this term is going to approach zero. However, that's only for first order parameters. If you're calculating second order parameters, such as variances, fluxes, atmospheric spectra, you have more of this sort of anatomy where you have to square that parameter. So then, while this term, this T prime noise is still mean zero, this term will approach zero when you average enough data together. This term here essentially forms a bias. It's squared, it's always positive. You average together, it's going to have a positive amount, and it's going to result in a bias in your data. And you can see that when we look at some of these here. If we look at spectra, everyone's seen noise floors in their spectra before. If you try to push to high resolution, this is a forward model here, but this, you can see that there's a very strong noise floor in this data versus the modeled data is this dashed blue line here, versus when you do an approach that I'm going to introduce soon here, you can remove that. And then similarly for altitude variance profiles of this LiDAR data, you can see that if you don't correct for this variance bias, there's this strong positive bias versus what the actual wave energy looks like. So traditional methods that you use to correct for this sort of bias, this is not a new discovery, this has been known for a long time, but traditional methods to correct this bias rely on you estimating that noise level and subtracting it from your data. So estimating what this term is and subtracting it out, or in subtracting it out. Similar with the noise floor, estimating that noise floor and subtracting it out. However, the issue with that is when you have really strong noise levels, you very often cannot accurately determine that noise. If you knew exactly what that noise was, subtract it and have perfect data. So obviously that's not a realistic case. So that's one of the major failings of traditional methods, and why this method I'm going to introduce in the next couple slides is very valuable. Also, just I want to point out here for these next couple slides, all of these derivations and these methods and the derivation of these parameters in general rely on the assumption of stationary ergodicity, meaning that a short time measurement of these atmospheric signals can be used to represent the means and variances of the entire atmospheric signal. So the interleaving concept is developed by Dr. Gardner and Dr. Chu in 2020, and this is essentially a new way to process your data in a way that inherently eliminates these biases and noise floors in your data. So essentially the way it works is you take your individual set of LiDAR data, say you have altitude and time resolved bins of photon counts. So instead of processing, normally what you do is you take all those photon counts and you would process them, process all your counts into one, let's say, temperature parameter. With the interleave method, what it proposes is taking those and splitting them into two bins, splitting the odds and even bins from each other and processing those separately. So that can be done altitudinally, or altitudinally like this, where you take your bins, you split them into two bins that are just barely shifted altitudinally, or you can do it time-wise, where you take them and you interleave them like this. And we say interleave because you need to keep these samples as close as possible. So essentially what you end up with is you end up with two atmospheric parameters, let's say TA and TB, that are measuring the same volume of space, but they don't share a single photon. They don't share a single photon count in common, which means that they do not share that random noise in common. So it's very critical to keep these separated as to keep the separation between these keep them interleaved as finely as possible. So if you had different altitude versus time resolution, you'd want to interleave them in the way that kept them as same volume as possible. And so to review this here, when we look at the variance here, if you were to calculate the variance like we showed earlier, you generate a bias because of this term right here, this T prime squared gives you a bias in your data. However, when you use the interleave method, instead of calculating variance, you would calculate covariance, or in a few slides, we'll talk about spectra. Instead of cross power spectral density, you would do or instead of power spectral density, you calculate the cross power spectral density. So while this term drops out, you still have a bias. However, when you look at the covariance, you have, instead of having this term here where you have the T prime noise squared, you have these terms multiplied by each other. And you can see here that these two are not going to correlate. That noise is random. The waves are real, organized perturbations. Same here, you have noise and wave. And then you have two different, this is the critical points, you have two different noises multiplied by each other. So each of these is going to cancel out when you average enough samples together. And it's very critical that to note that this only happens when you average enough samples together. So that is important to have enough samples in order to apply this interleave method. But the interleave method is able to inherently eliminate this bias without having to estimate and calculate that noise, as I introduced with the previous method. So that's the real advantage here, is that it inherently, through the processing, eliminates that. There's no, you don't have to assume a certain noise model. You don't have to assume a certain definition of that error or that sort of thing. It's inherently eliminated. So to demonstrate the need for this interleave method, if we look here, we can see a few examples I showed. This is real LiDAR data of interleaved EPM, which is a function of atmospheric variance or covariance if we're doing the interleave method. So to look at this winter first, you can see the dashed line is the uncorrected, the solid line is the corrected using the interleave method. You can see it's not too different for the winter data. That you may not even know that there is a bias in this data. However, it's definitely difference between these two. There is definitely a difference between these two results. So applying the interleave method has made a significant difference here. However, it's even more apparent when you look at the summer data, where we process it without the interleave method. You see incredibly biased results versus the interleave method yields a much more reliable atmospheric parameter, atmospheric energy parameter. However, there's no free lunch here. In exchange for this increased accuracy, the inherent elimination here, by splitting the photon counts into two different subsamples, you inherently lose precision in your measurements. So because you essentially reduce the amount of photon counts you have in your signal in half. So you have a noisier signal, which could explain why this gets noisy at the top. And some of the plots you'll see in a couple slides are especially noisy towards the upper altitudes. It's amplified by the fact that you've applied this interleave method. So again, kind of trade accuracy for precision with this interleave method. So in my 2022 publication, Jandreau and Xu 2022, which was published in response to the Gardner and Xu 22 paper that proposed the interleave method. That paper proposed time interleaving. This method tested out altitude interleaving using our iron LiDAR data, and also created a forward model to test out this method and sort of experiment with it compared to previous bias elimination methods and see how they all behaved in respect to each other. So I won't go too much into these other bias elimination methods, but you can see that one of them underestimates the signal. The other method we had previously used overestimates that energy. However, the interleave method, which is the green line here, estimates that purple line, the model's model wave energy, very well. So overall, the interleave method showed itself to be like a very powerful method. And also, Gardner and Xu proposed at the end of their paper that this could be used for atmospheric, that this method could be used for atmospheric spectra derivation as well, to derive spectra that inherently have no noise floor, which is pretty advantageous to having to estimate and subtract that noise floor. So especially when you have very low SNR data. So when this was suggested by Gardner and Xu, they provided this equation right here. And so when I was going to do some atmospheric spectral processing, I decided to apply it, and I could not get this method to work. Every time I tried it, I got larger spectra than when I started with. And so I came up with my own method. I came up with another method to apply the interleave method to the spectra that I found did work. And I'll introduce one in a little bit, but let me give explain first why it didn't work. Is it was a coding error. This is towards the end of my McMurdo season. And I just flipped the order of operations. So instead of taking the this approach says you take the discrete Fourier transform of your two TA and TB, they call T odd and T even here. Take the discrete Fourier transform of those two, multiply them, average that multiplication product, and then take the complex magnitude of that. I had switched those two, and so I was taking the complex magnitude before I was averaging, which of course wasn't going to work. I just did not catch that in my code. And so when I got back from the ice and reviewed with Dr. Xu, she caught that, and we realized that this method does work. However, I had already figured out another way to apply this method. So now we were left kind of an interesting situation. Yeah, incorrect. We have kind of interesting situation where we had two different ways to apply this method. And so we went and we compared the two. Let's see what the differences were. So the method that I proposed was a much more, it was to take the co-PSD, the co-spectrum of the power spectral density, which is the real portion of the CPSD, which is essentially the spectral counterpart to covariance. It shares a lot of similarities with covariance. They retain the same energy as each other. And this method truly does have no bias. However, it loses a little bit of energy. I'll talk about that more in a second here. The method proposed directly by Gardner and Xu was taking this magnitude of the CPSD, which is more the direct application of the interleave method. You compare it to how you generally calculate PSD, which is the complex magnitude of the DFT squared. So this is the more like direct application. However, we found that this one actually still has a reduced bias, which I will introduce again in a second. But essentially, when you take that magnitude, you lose a little bit of energy about this complex CPSD, and it results in bias. So if we look here at the anatomy of the CPSD term, okay, no laser. If we look at the anatomy of the CPSD term, you can see that there's a co-spectrum portion and a quadrature portion. The co-spectrum essentially represents the portion of the energy between these signals that they share where the signals are in sync with each other, and then the quadrature portion is the energy that they have when the signals are shifted from each other. So each of these signals, you can consider the noise in this CPSD to be split between the two of them. So when you calculate the CPSD, you expand it as shown on the screen here. You end up with your signal terms. You have the co-spectra and the quadrature spectra term, which are the terms you want. You have these two terms, which are still mean zero, because that noise term, they're going to act as noise. But then you have these bias terms, which are formed the exact same way as we saw them formed earlier. So ultimately, this should be a significantly reduced bias from what you had before you apply this method. It's very significantly reduced bias, and I'll show that on the next slide. However, you still have some bias terms. And even if you average a ton of samples down to reduce these very small, they are still present. Now, the other approach that I figured out after I couldn't figure out how to use the equation from Gardner and Chu, that co-PSD, the co-spectrum PSD, you only take the real portion. You only have that co in the delta co, so you don't have any of those noise terms. There's no bias terms in this data inherently. However, you do lose any energy loss in that Q term. Now, if your data are very finely interleaved, the energy in that quadrature term should be very small, so you may not have very much energy loss, but you do lose some. However, there's actually Dr. Chu and I derived an equation by which to correct for that lost Q energy, so that can be compensated for. So that's the difference between these two methods. We can also see it maybe a little bit better when we look at it graphically. So those are the same equations with the same color schemes that I showed on that last slide here. But you can see here, when you compare the two methods right against each other, red here being that magnitude CPSD, green being the co-PSD, when you compare the two right here, you can see without bias correction, we have a giant noise floor. Both of them do a very, very solid job at removing that noise floor. However, when you look at it at a zoomed up scale, you can see that there is a reduced bias still in that magnitude CPSD term. Because of those extra bias terms that are right there. And your co-PSD does a much better job at approximating that modeled spectra you can see in that slope curve right there. However, something kind of interesting about the co-PSD is you can end up with negative spectral energy, which doesn't have any physical meaning, but is essentially just due to the noise. So if you come through and you fit a curve to it, like you can see we have a dashed green line fit, does a very nice job of approximating that modeled spectra. And also, if you look at it in the log-log scale, you can see that even clearer. You can see that noise floor much clearer in the magnitude CPSD approach. And if we were to, this is not a good line fit, but if you were to attempt to fit a line to that region, you can see it's going to show you a much different slope than if you fit a line to that same region using that co-PSD method. So ultimately, we decided that the co-PSD is the better approach for if you truly do want no noise floor, absolutely no noise floor in your data. However, you do need to come back in and correct later for that, missing Q energy. So that's what we show right here. I went and derived an equation to correct for that missing energy based on just some of the basic principles of Fourier transforms and the cross power spectral density term. And it's a pretty straightforward correction. As I mentioned, this co-PSD is kind of these direct spectral, the direct spectral counterpart to covariance. So in Dr. Gardner and Chu's paper in 2020, they derived a correction term for their covariance, very similar term that can be derived for the co-PSD. And you can use to correct that lost energy. And another thing that we derived for this, the paper that all the spectral stuff, I didn't mention this, all the spectral stuff is in a paper that Dr. Chu and I have under revision right now, Jandreau and Chu 2024. But we also went and derived, I mentioned earlier, this whole method depends on those cross terms canceling out. I mentioned and tried to emphasize that you have to have enough data averaged together for those cross terms to go away. Otherwise, they're contributing a significant amount of noise to your result. So we derived we derived a relation between the ratio of the noise you have to your signal and how many samples you need to average in order to eliminate that noise. So that's this equation that we have right here. So for example, if you had a 20% ratio of your noise to your wave terms, it would take 64 samples to reach 5% uncertainty. And then if you had 40% ratio in those terms, it would take about 250 samples to reach 5% density. So, or 5% contribution of the uncertainty from these terms. And that's not total uncertainty, that's just contribution from these cross terms that if you average more data will slowly approximate to be zero. So this paper, Jandreau and Chu 2024, is, like I said, still under review. You might notice there's no precision equations here. We're still going over the uncertainty and precision equations, reviewing them with some good help from reviewers that we had, gave some very nice feedback. So we're going through those, and hopefully we're going to get that paper out pretty soon. One moment. So I bring up the Confucius quote again, because now that I have sharpened my tools, it is time to apply them. So The McMurdo data set over the years, again, over 13,000 hours of data spanning over almost 14 years now, has provided many opportunities for different climatology, case studies, and characterizations of these McMurdo gravity waves. So I got listed here as by no means an exhaustive list of the McMurdo gravity wave studies, but here are quite a few of the critical papers that were done to leading up to the work that I'm performing now. Over the years, the data has been revisited to recalculate climatologies as new data is captured and introduced to that set, as well as new methodologies being developed. It's time to revisit some of these, recalculate them using these new methods, and make sure that those agree, and see if there's any new discoveries that we can find in that data. So all those climatologies and characteristics have allowed us to put together a very solid picture of the McMurdo gravity waves. And so I've cataloged them here. There's a lot of information on the screen here, but I split them between their middle atmosphere properties and their atmospheres. That the middle atmosphere, so stratosphere, mesosphere results we get from about 30 to 70 kilometers, as well as the MLT we get from about 80 to close somewhere around 110 kilometers. And the reason I split them into these two portions is because I'm mostly trying to study with this work is how these waves develop from the lower to the upper atmosphere. And the main thing that you see when you compare these results here is the difference in wave properties between the middle and upper atmosphere regions. One of the main ones here you can see is if you look at the horizontal wavelengths right there and right there, you can see that they're very, very different between these two regions. And of course, they would change as they propagate from one region to the next, but these are so different that the general consensus from many of those papers I showed in that last slide over the years and what we believe now is that these are different waves. They have different wave sources between the middle atmosphere and the upper atmosphere. The leading theory for that right now is that these middle atmosphere waves are breaking somewhere in that region, developing secondary gravity waves, which have larger scales that then propagate up into that MLT region. And before we were not able to explain how these waves in the MLT region could have the properties that they did, but this theory and modeling backs up that theory to support that this may very well be the generation method for these gravity waves we're seeing in the MLT. So it's a very interesting, poses a very interesting picture of what we're seeing in the McMurdo atmosphere. So applying those interleave methods to gravity wave EPM allows us to generate new figures. So the main thing of the EPM, the main thing of the interleave method contributed to the derivation of these parameters here is that it allowed us to push the winter time, which is here we got winter, spring, and fall. It allows us to push the upper boundaries of the winter EPM measurements we could do. EPM again being gravity wave potential energy density, essentially the strength of these gravity waves. We were able to push that up to close to 70 with pretty good confidence in it, whereas before pushing to 65 even was stretching it. We weren't as confident in the results. So now we're able to push even higher than that. And in the summertime, we were able to push pretty confidently close to 50 with all the data. Summertime, we have very strong sun at the pole. So it's very low signal to noise ratio. However, this method allows us to continue to use that data and kind of recover some of it. So very valuable for this sort of study. So looking at this, the results we see here, they're kind of one of the most interesting things, I think, is when you compare it with the previous study that compared McMurdo middle atmosphere gravity wave EPM to upper atmosphere EPM. It was done by Liu et al. In 2015. And this was done long before we had, this was long before we had developed the interleave method, and we didn't have as good of an understanding of how these biases work. And so when this study was done, the bias correction method was not applied. Even though the winter data is not that strong, as I showed a couple slides ago, the winter bias is not nearly as strong as the summer. These results still are significantly different from the ones that we get now that we correct that bias. What you can see here is you can see that this gravity wave EPM seems to increase, picks up again at the MLT, almost exactly where it leaves off, which implies some strong dissipation and regrowth process in that region that we couldn't really explain. And as I'll show in a slide or two from now, we see a very different picture now. The other thing I wanted to highlight from these results, and these are still very preliminary, they've not been published yet, and there's still more we want to do looking into these, how we can improve them, but also how we can interpret what we're seeing. One thing that I seem to see is it seems to me that this winter data has two different regimes, maybe two different regimes or more of dissipation. So if you look at the scale height, calculate the scale height for the bottom half and the top half of this winter profile here, you get very different scale heights. The bottom half is like close to a 12-kilometer scale height. The top half is over 24 scale height. So and then that's not to necessarily say that there's some specific event going on at 45, but somewhere in that process, the dissipation appears to change. If these waves were not dissipating, they'd be increasing at the adiabatic growth rate, which are plotted in this black line here. So we do expect dissipation, but the reason why that dissipation is changing, I've not looked into yet. So that's something I do want to look into. You sort of see the same thing in the spring data as well, but not nearly as confidently. So to do that, I may want to look at how these EPMs are resolved from gravity wave resolving models of like WACM and HIMCM. So then, as I mentioned earlier, we can also use the interleave method to derive atmospheric spectra. We were able to do this before. We didn't run into noise too often, but what we're able to do now is we're able to confidently push the resolution we could derive these spectra at a little bit higher than we previously could, as well as get a much more concrete and certain derivation of the summertime spectra, which due to its noise has always been more of a problem. So when we derive these spectra, we see the expected power law dependencies of omega of -5/3, close to -5/3, and vertical wave number spectra close to -3. So look at the vertical wave number first. We see close to that -3 slope. This is, by the way, when we fix the linear portions of these slopes, of these profiles, you see that close to -3 slope in the wintertime, although it gets much shallower in the summertime, as you can see over here on that summertime plot in most months there. And that's similar to results we've seen, previously published results from this McMurdo data set. And that's not out of the realm of possibility we would expect to see elsewhere in compared to other published vertical wave number spectra. And then looking at the temporal spectra, most of the slopes of that temporal spectra are close to that -5/3, that 1.66 -1.66 number that you actually see, which you got exactly in the winter. But there seems to be no general really defined trend in these here, in these slopes of these temporal, in this temporal frequency that we see. Although there does appear to be some trends in the, there may be some trends in the characteristic wave number, the omega star. As you can see, give me one moment, I need my pointer. Okay, yeah. So there does seem to maybe be some trends in the omega star that we can see here, which does fit with past, which does agree with theory and agree with past observations. So all these spectra, they're pretty preliminary, and they will also be requiring more study before we can make any concrete conclusions about them. But again, I just want to emphasize that the interleave method allowed us to derive some of these profiles with a lot higher degree of confidence than we previously could before we had to estimate that noise properly. Now we know they may be noisy spectra, but they're definitely unbiased. So the next major step in this part of the study is going to be processing the MLT results, the MLT data coming from our sodium and iron metal layers. Well, processing these is a lot more complicated than processing that Rayleigh data. You have more dependencies. The densities of these atmospheric metal layers, they vary over time. Sometimes within a single run, they can vary significantly. And also the signal return you get is incredibly dependent on accurate laser frequency, which of course we do our best to control. But it essentially means at the end of the day, there's a lot more data screening that has to be done to this MLT data before it can be processed. So I've got some initial results up here that I've done so far. My temporal frequency spectra looks, it compares well to previous results, but nobody from our groups actually published the vertical wave number spectra from this region of our data yet. And this, I didn't plot it here, but this is actually a slope of -4.3. So it's way, way steeper than we saw elsewhere, which leads me to, and that's been seen in other measurements elsewhere on the globe of this region of gravity waves. And so I think that this definitely just needs a lot more work before it can be publishable quality, but I just want to show that this work is underway. And the main thing I wanted to highlight here is this EPM measurement that we got here. And again, this MLT EPM, the upper region EPM needs a lot more data processing before these results can be final. However, you can see the very different picture as compared to what we saw earlier, where now it's almost more of a much more linear growth, and there's not that heavy region of implied dissipation. There's still a question mark of what goes on in this region here, which we can't derive as the O2 and N2 density have dropped off. We can no longer get a good Rayleigh signal, and the metal layer densities have not yet started yet. So that gap region has always been a question, but I think there's less questions about it now. And with further refining of the MLT EPM data, I think we'll be able to get closer at least to answering those questions. So this summarizes all that work has led into the main goals I have for this topic one, which is the climatology of EPM and spectra. So these goals, I'm just going to read them verbatim here because so what I'm proposing is I want to develop baselines of vertical profiles of gravity wave energy and spectra in the stratosphere, mesosphere, and lower thermosphere. And as you can see from the last couple slides, I'm already decently along with that process. I want to develop climatologies of these parameters throughout all seasons. And then I want to determine if that gravity wave growth rate changes in the winter, that scale height comparison I was showing, and then check if the models show that behavior. And if they do, I want to figure out what's causing it. So these are the next steps. And to do that, as I showed, I'm going to apply the interleave method to derive these climatologies. And if I do any model comparisons, I'm hoping to do so with the help of Dr. Liu and Dr. Becker. So on to my next topic here is that gravity waves have a very important role that they play in atmospheric mixing. So unbroken wave contribution, the contribution of unbroken gravity waves to atmospheric mixing is a very critical part of their contribution to global energy, heat, and constituent fluxes. Often when models do not fully resolve gravity waves, they do not resolve this sort of mixing, and they just parameterize the turbulent mixing, which is turbulent mixing, KZZ, as these models generally call it, that is induced by the turbulent breakdown of broken gravity waves. However, most of these models do not in any way represent the contribution of unbroken gravity waves. So these unbroken gravity waves, they do things like modulate gradients of mixing ratios. They induce transport directly via of heat and constituents via Stokes drift, and they affect chemical rate coefficients. So they're definitely not something we can neglect in our models. However, at the moment, we've not developed a way to model them. So Dr. Gardner has been working a lot on this and shown in some recent publications the effect of diffusion in the atmosphere, or diffusion-like processes in the atmosphere, when you consider this unbroken waves versus when you don't consider these unbroken waves. So Gardner and Chu 2022 released a paper. Chu et al. In 2022 released a paper studying this in the McMurdo data, looking at sodium flux and heat flux, energy flux from, I should say diffusions, I'm sorry, derived from these sodium mesospheric, lower thermosphere sodium data that you can see here. And one of the things that's very unique that this paper highlighted, and also there in Dr. Gardner's theory, is that the diffusion induced by these waves, by the organized motion of these waves, is very different than the diffusion that we're generally familiar with from a fluids perspective, where you have down gradient transport. You have high number density transporting to low number density. These gravity waves can, I guess it's not truly a diffusion, but it's a diffusion-like process where you can actually get up gradient transport, which is a very unique factor of these. And since KZZ, the turbulent diffusion, since turbulent diffusion cannot do up gradient transport, you can't just scale and modulate your KZZ value in your models to accommodate for this. So it's very important that we understand how this K wave, this is Dr. Gardner refers to this as K wave, and KH are your constituent and heat diffusion, your constituent and thermal diffusion parameters. You can't just modulate your KZZ to make up for these because they don't operate the same way. So it's very important for us to understand what these look like in the atmosphere, how they respond to different background atmospheric changes. So what I'm proposing here is to develop a climatology, use the relations that Dr. Gardner developed or derived from the dispersion and polarization relationships in order to derive a climatology of this K wave, KH, and compare them to KZ in the McMurdo atmosphere for both the MLT and the stratosphere region. This is a very preliminary result that Dr. Chu was able to put together. However, actually doing this in a confident way and doing it on a climatological scale for all different seasons is going to be a much larger task. So that's the work that I'm proposing to do here. I want to calculate these wave-induced diffusivities and determine how they vary in the stratosphere, mesosphere, and lower thermosphere over McMurdo, and again, how they vary throughout different seasons and in response to different background conditions. And so this work is obviously going to be done heavily in collaboration with Dr. Gardner and to keep these, it's going to be done in collaboration with Dr. Gardner to calculate these parameters. So the third topic I've got here is that of multi-step vertical coupling. So this is what I mentioned earlier. I talked about some of the new developments in gravity wave, how we consider how gravity waves behave in the atmosphere. And one of the major ones is that when these gravity waves break, they generate secondary gravity waves. So as gravity waves propagate up through the atmosphere, they break and distribute their energy, diffuse their energy to the background flow as a wave drag. However, often these waves will break and deposit such an impulse into the atmosphere, they'll generate what's called a local body force. That local body force will generate its own gravity waves. Now, some of these gravity waves are small scale due to instabilities within that breaking process, and those will not make it, those generally, we don't believe that those generally propagate very far from the source of that local body force. However, the larger scale waves that are generated by that local body force can propagate upwards in the atmosphere and undergo their own breaking processes and generate more gravity waves, or they can propagate up to much higher altitudes in further reaches than those primary gravity waves could. So this is the process called multi-step vertical coupling, which was coined by Dr. Becker and Dr. Vadas. And their models have shown that it plays a significant role in governing, especially the upper regions of the atmosphere, and how that wave breaking deposits energy into that region. So the McMurdo ladder data has been used to support this theory. In 2018, in 2018, the LiDAR data from the McMurdo iron LiDAR was used to validate the first observation of such a local body force in the form of this fishbone structure, where the model predicted this sort of structure if you were located downstream from that local body force. And we saw that same structure appear in the LiDAR data. So this is the first observational confirmation of the local body force occurring in the atmosphere. And as I mentioned earlier, this multi-step vertical coupling is kind of critical for interpreting our LiDAR data. As I mentioned, that middle atmosphere region is different from our upper atmosphere region. At the moment, one of the only ways we have to explain that is this process of multi-step vertical coupling. So not only can our LiDAR observations help explain this multi-step vertical coupling, but it can go the other way around as well. So like I mentioned, I showed an example in the last slide of how LiDAR data can be used to study this multi-step vertical coupling and secondary wave breaking. This is another example from Chu et al. 2022, where Dr. Chu and Dr. Gardner were able to derive, they derived some potential energy profiles for the upper atmosphere. You can see from around 80 to 115. This is actually derived using the interleaved method that was able to extend a couple extra, almost like 10 to 15 extra kilometers in range, altitude range, because of that method. And when we do that, what they actually found is that this EPM profile you can see over here is EPM profile you can see over here is actually very similar to this one modeled by Dr. Eric and Dr. Beckus and Dr. Becker and Dr. Vadas in their 2019 paper. You can see it's very similar around the same altitudes. Even you have this dip where the energy decreases and then begins to grow again at a faster rate. That also corresponded to a region of high downwards wave energy propagation. So this is it's pretty likely that this is a case of secondary wave, this is a case of wave breaking and that secondary wave generation and growth that we saw in our LiDAR data. So it's just an emphasis of how the LiDAR data can be used to study that wave breaking process, and how, especially how the interleaved method can facilitate that those observations. So to date, there has not yet been, while the models have shown much evidence of tertiary waves, that's where tertiary or higher order waves, that's generally when you see this wave breaking process occurring in the thermosphere or the upper mesosphere at least. But we've yet to see observation of this in LiDAR data like we've seen from that data I showed earlier, which was in the middle atmosphere. So we've yet to see observation of tertiary wave evidence, and conversations between myself and Dr. Vadas have emphasized that seeing this would be, finding evidence of this would be very valuable to back up that theory. And we have not yet done a full thorough search of both the iron and sodium regions of our data. Again, 13,000 hours, there's a lot to go through. So what I'm proposing is that I'll be going through that data and processing it to see if we can find any evidence of this tertiary wave. We've seen some interesting things, or waves disappearing, or not disappearing, but like dissipation processes going on where you see sort of similar structures that we saw before, but nothing yet has been confirmed to be tertiary waves. And another interesting aspect of this is that I didn't talk about the metal layers much themselves. I won't spend too long on them, but essentially the metal layers are formed by incident ablated cosmic dust and meteorites. They form a pretty permanent layer between close to 80 to 100, 110 kilometers. However, these thermospheric extensions that were discovered over McMurdo and have since been observed elsewhere on Earth allow us to push, with careful data processing, we can push the boundaries of that and actually observe gravity waves up to 150, 160 kilometers. You can see in some of these results right here, you see some gravity wave structures reaching up significantly higher than we previously could observe them in these persistent range of these metal layers. So what I propose to do is a couple case studies where I look at and analyze gravity waves in this thermosphere ionosphere sodium layer in order to look for signatures, if not wave breaking like we saw with the fishbone structure, at least downwards phase or upwards phase progression, or downwards phase or downwards propagating gravity waves in this region of the atmosphere. So again, what I propose here is to, with my third topic, is to find the first observational evidence of tertiary waves in the McMurdo data. And if we find these, to characterize them and see what they can tell us about wave breaking in this region. And that'll be done with the work, heavy collaboration with Dr. Vadas and Dr. Becker to compare with their models and identify the source of these waves if we're able to find them. So those are the main topics I want to study for my PhD that I'm proposing. I wanted to propose a few wish list topics, and these are related. These aren't just random things I want to accomplish during my PhD. These do tie into a couple of those previous goals. So a lot of those goals you might notice were kind of related to the topic of vertical coupling. One of the things I would like to look at is that horizontal coupling as well. And in 2020, I was able to contribute to a study our group did into studying the relation between McMurdo gravity wave energy and the QBO, the quasi-biennial oscillation, which is an equatorial process. We found that the gravity wave energy at McMurdo was higher during easterly phases of the QBO. I should specifically say wintertime gravity wave EPM higher. Winter. wintertime graduate EPM is higher during easterly phases of the QBO. We found that three phases of easterly QBO were studied. We found pretty good correlation between this. And my contribution to the study was to analyze MERA2 data to look at the relation of the polar jet and zonal winds in response to these QBO phases. And we found that there was difference that we saw in the southern hemisphere versus the northern hemisphere. So the northern hemisphere relation between the QBO and the polar vortex is very well known. It's the Holton, referred to as the Holton-Tann effect. It has to do with the QBO modulating northern hemispheric wave guides, directing planetary waves into the vortex and disrupting it. But that process is different in the southern hemisphere because of the difference in planetary wave behavior. And so that the direct relation, while this study identified a direct relation between the QBO and the polar vortex, that being that the vortex in the southern hemisphere expands during easterly QBO phases. We've got to figure out the exact mechanism by which those relate. So studying that mechanism itself is a little out of the picture. It's something I would definitely like to do, but that could be most of a PhD in itself probably. So what I have done is I've taken our data and I've extended that. Since we've collected 3 or 4 more years of data since that 2020 study was done, we've collected quite a few more years of data. And what I'm hoping that I'll have time to do during my PhD is to study that horizontal coupling and incorporate this new data into that study. So I've already processed a lot of this data and compared it with the relation of the QBO and the INSO, the El Nino Southern Oscillation, to see what those relations are. And this study has not gotten, I've not gotten very far into the study yet. However, we've seen a few interesting things already, such as that this newest year actually shows the highest EPM we've seen. And again, this data could probably use some more processing and refining to make sure we trust those results. But so far, it's showing us a higher EPM than we've seen, even though it's not in that easterly QBO phase. So that's interesting. It may have something to do with the fact that it correlates with the very strong INSO phases like we saw in 2015. However, that last study we did not have nearly, the INSO is a pretty long phase process, quasi-periodic of 5 or 6 years or so. So with that previous data, we only captured a couple cycles of the INSO. So now we've captured another cycle of the INSO. So we may be able to derive a more significant correlations between that and investigate the relation between those more. But again, this is a stretch process. I recognize the limits of what you can actually include in a dissertation work. And then finally, I won't spend too long talking about this, but I would also really like to dig into wave drag as well. Dr. Gardner was able to derive, again, using the polarization relations and polarization and dispersion relations, a way to derive wave drag from the EPM, from that EPM that I calculated in my first topic. So if I'm able to characterize the EPM, I'm only a couple steps away from calculating the wave drag in theory. It's not nearly that simple, though. The derivations specifically for wave drag require a monochromatic assumption, so it's a very case-by-case basis. It would not be able to do a large climatology of wave drag without serious work. And also, we need to incorporate external horizontal winds. And so we were able to collaborate with Dr. Scott Palo and get his meteor winds at McMurdo. So we could get real-time, background winds to determine the direction of wave propagation and all that to calculate this wave drag in order to get directional wave drag. So that would be another stretch goal of this dissertation. If there's time, I would like to calculate this wave drag. So ultimately, summed up all those goals that I mentioned earlier here. And here I can come back to the slide too if anyone would like. But also this is my work plan. So what the schedule I'm proposing is to kind of work on these in the order that I introduced them, and hopefully have my work done by the end of the summer or next fall and defend by that point. So I have a couple. I can come back to this slide as well if anyone would like. But I've been lucky enough to be co-author on 2 papers with Dr. Chu and other members from our group, and then have one first author paper myself, as well as another one that's currently under review with I worked on with Dr. Chu, and also had the opportunity to go to plenty of conferences. Very blessed to have been able to go to all of these and share my work and network with everyone, and also been recognized by Ceres multiple times, a couple times for different honors awards, as well as received NASA Future Investigators Grant in 2022. That's currently funding my research. So with that, thank you guys for listening to my proposal. I hope you have some good questions for me.
Okay, thanks very much to Jackson for a good presentation. Now I think the floor is open for any questions from the public. Afterward, we'll have a closed door examination, and if anybody wants to, take a break, it's fine. Do you have any questions? We still have some water. Do you want some?
Yeah, I've been thinking about this interleaving method.
Mhm.
So, of course, I've never heard about anything about this before, but usually when you do some approximation, either in math or in numerics, you have an increment, and then the whole thing converges when the increment tends to zero. And you said that the shift between the two samples has to be as small as possible.
Mm.
But what is when the shift is zero, when they are identical? How do you then get rid of the noise?
I mean, if you were to truly shift to zero, generally when you're applying to your real data, there is a minimum shift that you could do, right? Because the minimum resolution at which you captured your data. So if I'm only capturing data every 3 seconds, that's the minimum I could shift it. If you, of course, you could minimize the noise is introduced at the photon counting. So if you were to increase the resolution at which your LiDAR or radar was collecting data, you could approach that 0 point. And as long as you were truly not sharing any counts in common, they would have independent random noise, and you could still apply it. And I should also introduce that you can actually, I think what Dr. Chu was about to say is, optimally, you would do this method using 2 independent LiDARs. So 2 independent instruments right next to each other, where you would truly have a delta T or delta Z of 0. So optimally, you do that. But what this method, generally, that's not cost efficient to have 2 separate LiDARs or at least 2 receivers. So you could apply it like that. I actually think that there's the LiDAR group at University of Alaska Fairbanks. They have 2 separate receivers, and I actually do think they may be doing something like that, where they're using 2 receivers to do it. But yeah, thank you. That's a good question. I meant to mention that.
Are we starting the?
No.
Yeah.
Do you have any questions?
Yeah, I was wondering, like, what the relative magnitude of that active loss by the calculation is, like, compared to like type of energy that you calculate, and then also when you're estimating anchor for that, how can you ensure that's more accurate than, say, estimating and calculating the noise floor when you're trying to reduce bias that's introduced by tradition?
Yeah, no, that's a good question. How can you? What Ari asked was, how can you? One, how much is that correction that you have to apply to the co-PSD or the covariances? And then 2, how can you be sure that, since you've had to apply some correction, how can you be sure that how can you ensure that this interleave method is more accurate than your like subtraction method or something like that? So to answer the first one, in Gardner and Chu 2020, they dive into exactly what they do some calculations on what exactly the percentage is of that covariance underestimation of your variance. And if you keep at the resolutions we're looking at 1 to like less than 1%, around 1% of a difference, so almost negligible. However, it's a little more complicated when you look at it in the spectra, because when you have that shift, say you have a shift of 48 meters, which is like what we have in our data, as you approach the resolution of that shift, so you're looking at like a vertical wave number plot, right? It's increasing in frequency as you get towards the right side of the plot. You actually have a function of correction. It's not one, essentially your correction is frequency dependent. So at higher frequencies, as you approach that delta Z amount, as you approach 48, the resolution of 48 meters, say, that correction is going to get larger and larger because each of those bins is missing more of that noise. So it's essentially it's frequency dependent in the spectral application. It's a little more complicated. I can show you the equations later if you're interested.
And you have that forward.
Yeah, and I've done, yeah, and we've done forward modeling too to confirm that, since just to confirm that our corrections and some of the calculations were accurate.
Nate, do you have a question?
I think not right now.
Okay, yeah, thank you for attending this presentation.
Thank you, guys.
Yeah, we're going to have a closed door presentation. Yeah, thank you. You guys want a break?
Yeah.
Yeah, go back.
Yeah.
Yeah, can you stop this recording?
Yeah, I will.